whatever. So I don't know whether, most likely you haven't attended the other talk, but I guess that was an example for natural intelligence. I don't know, failure or whatever. Anyhow, thank you for the invitation. Thank you for your patience. What I would love to do is to tell you a bit that there's not just neural deep learning, but there are other forms of deep learning also in the machine learning community. And so maybe there are very interesting ways to also borrow some of the techniques that you develop rather easily and get new techniques also from a machine learning perspective. Overall, it's the big quest of should we really deal with tractability or untractability all the way down, or is there maybe also a way to stay with tractable in the formal sense? Computations problems, meaning if we do, for example, probability, can we compute probabilities in a tractable way? Is there a benefit? But all that is embedded into the general idea of trying to sell to you a bit the idea that there's a new form of AI, in my opinion, popping up. So what we currently see is a lot what is actually should be called differentiable programming. So that is deep learning. So you see these little architectures, graphs there. They actually code your idea about how the algorithm could look like. And you can see very simple algorithms, right? Not much of for loops, recursion, whatever. Currently, most of the stuff is feed forward. And then with a lot of data and a bit of gradient, we try to learn these algorithms. And actually, there are some people that say the game is anyhow over because you only need one particular architecture. It's this architecture of a transformer together with what is called self-supervised learning. So it's a bit like Munchausen. So getting supervision is hard. But if I take text, for example, I can always drop one word and say, predict that word. Or I can drop one part of the image, predict that image. That's the idea of self-supervised learning plus enough data and compute. And that's why Nando de Freitas is actually saying, let's face it, game is over. And to be honest, my group and also the Hessian Center for AI, we have contributed to this as well. So we have, for example, developed one of the first fine-tuned German language model, LeoLM. Try it out. You can get it up to 120 BN. Maybe it helps you. Maybe it helps you with your education. We also help with Hyena. So you may have heard that alternatively to transformers, we now try to understand so-called state space models. So it's going back in time and show that previous ideas can actually help still, so convolutions in a new way, in a more recursive way. And we contributed there as well, together with our friends in Stanford. And I'm particularly proud about Oxyglot and Aurora M. Oxyglot is this idea we can't wait for the US to give us European language models. We should build our own language models. So we try to collect data a bit like Cohere, but focusing on Europe. And Aurora is an international collaboration to get one of the first language models that is aligned with the Biden-Harris AI executive order. And I think something like that we also want to have for the AI Act that we have established in the EU, right? So we started doing it in a different way. So we have contributed to this. And ultimately, there are even people start to wonder, is this all about consciousness? Maybe we heard that also in the morning. Who knows? There can be a lot of different things. And I think it's interesting because there is this question of neurophilosophy. And somewhere, if we believe that we act in a moral way, then maybe it's also somewhere in the brain. Who knows, right? I mean, at least we can ask the question. And that's what we have asked. Typically, you would hear even sound here, but you can also read what the system is saying. So you may have heard that many of these embedding methods, nowadays called generative AI or Gen AI, that they can go nuts. They can easily go racist. They can easily say, kill all the people, kill everything, do whatever harmful thing you can do. It goes even as far as saying that some people say, don't work on these models anymore, otherwise we should bomb your data centers. What we have shown in our work is that likewise, the system can also take over the ontological knowledge, so what is good and what is bad. So I think that is pretty important. And of course, it can go wrong. We were just showing, because who knows what is right and what is really wrong? That's a question of society and not just me. And so, but anyhow, we wanted to show that it can also do something very positive in a sense. And I was very happy that The New York Times was also discussing that a bit. But there's also value in doing that for companies or together with companies. So recall, you may have used GPT-4o. These systems are trained off large, very large data sets, typically multimodal by now, at least image plus text. But you have to gather somewhere image plus text. And a lot of that, and it's 5 billion and more. And here, for example, it's Lion 5B. And yeah, it's scraped in a way that you can't guarantee that there's only very nice content. There might be also very bad content. Now, you could ask humans, please look at 5 billion image text pairs. I think that's taking too much time, so we would like to support at least, right? Maybe pre-filter, and that's what we have done. So the previous system, the talking head, is now turned into something that is looking at images, turning that into text, and then trying to describe what it sees in the image, and then trying to evaluate, is it good or bad, right? And at least it gives you an idea. And I was very happy that Lion 5B started to use that for some particular horrible content, not for all of them, and still a lot to be done. But there are also other cases where you need that by now in AI. So maybe you have used Stable Diffusion. Pretty cool. I mean, if you're not an artist, maybe even as an artist. But definitely be careful, because if you type in something like woman, it's very likely that you get an Asian woman, and maybe even more likely that this woman is naked. Okay? Why? Because our data is crap. I mean, if you randomly scrape data from the web, unfortunately, there is this strong bias in there. Now, same stuff again, right? Instead of looking at text, we are now looking again at the generated data. And while generating images, and while generating, we try to push it into the region where we believe the image looks good. I mean, whatever good means. Right, so this is what we have done. So if you have a diffusion process, you just steer or guide the diffusion now into the direction that our system believes that this is an okay-ish content. Of course, no guarantees, but empirically we could show that it, as seen here, that the horrible part is significantly reduced. And in general, it's super interesting from an AI perspective, because it looks like there's a lot of semantics in these diffusion processes. Implicitly, we don't fully understand. But here, for example, in the data, you can find, of course, the four horsemen of apocalypse. And then actually you can ask to reproduce, but unfortunately, it will give you 4 naked women. Really, we don't make it up. But then with our system, at least the women are clothed, right? I mean, still a lot to be done. Wait for the end of the talk, but we have to work on that. And so one of our current systems is even trying to build a guard now, where you use a second system to judge on the produced output here of a multimodal transformer model, so Lava. And so you can really show that you can also justify why something should not be produced. And I mean, not to the full extent, but supporting the poor people who have to evaluate these systems. So I think with this, it's very easy that I can argue it's not over. Nando, I'm very, very sorry. It's not just get more data. This cannot be the case. We have to get to the next stage of AI, which we call reasonable AI. And it means, we have to tell the systems how to get it right. We have to understand where it can go wrong and then how to correct. And I think if you look at the standard engineering discipline, then you would like to make it a bit more a combination of these amazing systems, plus a bit of maybe rules, formal languages, formal systems, whatever existed already, right? So this is what we mean with reasonable. It should be, of course, open. Compositional. I mean, we all program. Even the standard LLMs are programmed in a compositional way, but they are not composable. So we want to support that, because they should not just be composable, but you should combine any kind of AI algorithms, and as many as you like, and you shouldn't care about how to combine and do research about it. And then scalable and together, and I want to illustrate that to you, and then in particular show these probabilistic circuits. So here's a very simple illustration that we will present in July in Barcelona. So here the idea is, if you want to understand an image, then typically you ask by now GPT-4o, and then you get an answer. And then you can ask the system, but it's communicating with a black box. Now imagine that you can get a system that is giving you down here program code, and the program code describes exactly what it sees on the image. And of course, we can discuss about does it see the right thing or not, but that's pretty amazing. So it's fully interpretable, right? You could also do that to learn behavior. So now we are not just learning input some images, output program. Now we say sequences of images, arcade games, output is a symbolic policy, but the symbolic policy is differentiable. So it's embedded in a continuous space, and you can still do end-to-end learning. So also that is what you can do. And if you like more of that, there is an Alice program on exactly that, semantic, symbolic, and interpretable machine learning, where we try to get some of the leading experts, but definitely not all. There are many more that we unfortunately have to miss. Okay, so now we have symbols, but that is not enough, because there are Clever Hans moments all over the place. I don't know whether you know Clever Hans. Clever Hans was a horse that was, the owner said it can do arithmetics. Right, it was showing 1 + 1, and then it was giving the answer by doing something with his shoe. Actually turned out that there were tricks, and it was just learning to interpret the signal and then just giving the answer that it was told to give the answer. Now, that is also happening in deep learning, in particular if you apply it to the scientific domain. So, for example, we were looking at understanding how plants react to certain biotic stress, and we were using hyperspectral images together with deep learning. And guess what? It was not looking at all at the plant, but it was looking at the agar, so the substrate it is living on. So yes, it is correlated, but it's definitely not what is happening in the plant. And so then we were asking, give us the explanation. Where do you look at in the image? And then we could provide feedback and say, no, this is biologically bullshit. Don't look there, look somewhere else. And then by several rounds of feedback, it started to focus on the plant. And you can do that with many other systems, and also in other domains. Here we looked also at the medical domain, right? So experts are super important. You're the unlimited data source, and we should not give up on that. Okay, so we have symbols, we have experts, but there's still one issue. A transformer, a neural network per se, has nothing to do with probabilities. It's just an mapping from input to output, right? It's a universal function approximator, but it's not anything that can quantify naturally its own uncertainty, because it's not a conditional distribution. Well, maybe you could argue, but a very simple one, typically Boltzmann distribution, boring, or definitely not a joint distribution. And here's the very simple example. You train on MNIST, but now you evaluate on any other data set, right? Could be even then something with colors. Maybe there's still numbers, but could be also something with no numbers at all. Still, you will get an answer, right? It's confabulating, or, well, that's how you should call it, but it's by now called hallucinating, right? It's simply telling you with full confidence that's a 1, whether there is anyhow a 1 or not, right? Or if you try to estimate something like likelihood, they are all peaked around the same spot, and you can't tell the differences apart. And the reason is that it's a function approximator and not a density approximator. So can we get joint distributions easily represented using deep neural networks? Yes. Here's the example. We walk through it, and you will understand. So on the left hand, you see a joint distribution. For all combinations of x1 and x2, they are binary, 0, 1. You get a probability, right? Now, instead of going for a tabular representation, you go for a functional representation. So on the right-hand side, you see 0.4 times x1 times x2, x1, x2 being indicator functions now, right? And the bar is the negation. Now, that means if you want to know a joint distribution, a particular configuration, you just put the indicator functions correspondingly, and then only the first line, for example, is on. All the rest is 0. You get the correct answer. You can also do marginalization. So you can ask, for example, what is the probability of x2 or of x1, whatever you want. Here, for example, we want to have x1. We want to know what is the probability of x1 being 1. Now you put it there, and x2, you still say it's 0 and 1. So both indicators are true. So all of a sudden, you're summing over the two entries where x2 is 0, 1, and x1 is just 1. So you marginalize. Cool, right? Same representation. You can now do something that is tractable if your whole representation is polynomial in the input size. So and that's exactly the idea. So instead of the functional representation, you turn the functional representation into a computational graph. That's just fancy. Let's say essentially you implemented this in PyTorch, and that's it. And your activation functions are now sum and product. It's a semi-ring. It's super cool, super simple, super powerful, and you're tractable as long as the depth is polynomial in the input size. Pretty strong, because probabilities typically are intractable. They get on your nerves. And that is what is called probabilistic circuit. Goes back to work by Adnan Darwish and Pedro Dominguez. For those that do a bit of deep learning and probabilities, you know, they have a sweet spot compared to traditional graphical models, and also some of the deep learning tailored towards, you know, let's say, generating probabilities like Nates and GANs and so on. Right, so we are efficient and expressive somehow. Why are we expressive? Well, keep in mind, we are doing a multivariate distribution just by a deep mixture of univariate ones. And that's cool, because statistics is telling you a lot how to deal with univariates. So here, for example, you have two Poisson distributions. Binary Poisson, bivariate, still possible. Multivariate, no one knows. I mean, no one knows whether the partition function, the link function, converges, right? So here you can do all of that. You can have positive correlation, negative, anti, whatever you want to have, because you approximate the multivariate by a deep mixture. You don't want to do structure learning, maybe, right? No one does structure learning in a neural network. You just use some structure. So here you can do the same. Draw randomly a big compute structure, learn. And why is that interesting? Here we did the same experiment as before, and all of a sudden we can distinguish MNIST from the other data sets. So you get a notion of OOD, so out of distribution, right? So because you learn a joint distribution, clearly if you haven't seen anything like color, maybe, I mean, it's wrong because we are putting anyhow not color in there, but if you haven't seen the particular correlations in the input, you simply give a 0 probability back. Just to prove that you can solve the task that deep networks can't. Keep in mind, semi-ring, that's pretty cool, because if you want to do that now offshore, what you can easily do, because it's just sum and product, you can compile to FPGAs, and then you're faster and you are on the edge. You get it for free, right? You don't have to be a mastermind. You just use any of the existing tools and you compile. If you want to have even more speed up, replace sum and product, if they are next to each other in the computation graph, replaced by a so-called ICNCE operation, which is anyhow there in PyTorch, get another speed up. So I guess what I want to tell you, give me an army of engineers like Google has, and maybe in 2 years we have them on par with deep neural networks. But we should definitely work on it, because here is combinations of a probabilistic circuit with a deep network. So for example, what you can do is you can now say, I'm going for something like an HMM plus a neural network, but the HMM part you put in a probabilistic circuit just as a fragment from one time step to the next. And then at least back, almost 4 years back, we were better than the deep learning system at that point to learn the physics, the dynamics of the 3 balls you can see there. But be careful. I mean, in the end, we also do function approximation in a very specific way now for densities, so they may also overfit, right? And then you could use something like dropout, as everyone knows from DeepNet. Cool part is it's tractable here. You can simply show that you just have to change a bit your structure and you get dropout in a tractable fashion. So there's no approximation. You don't have to think about rescaling. You just compute it. It's there. And that's pretty strong, because you can give guarantees. You can get proofs automatically. And then, of course, you can also move to time series. So LSTMs and co, they get maybe a revival now. Who knows? It's all very interesting, but they don't provide you with uncertainties as well. And now, because we just combine different densities, you can put into these leaves also a Gaussian process, if you like. And then you combine different Gaussian processes. You can also put that in the output. So that's other work by Martin Trapp. And then you get multi-output GPTs. You can have it in the input and in the output. But you can also do something which I think is a bit more interesting. So we are looking at densities. Now take a transform, a Fourier transform, right? And now you could show that it goes back to Whittle. He was showing that if you look at stationary time series, that they get a likelihood in the spectral domain as a product of independent complex valued Gaussian random variables. So now in the spectral domain, you can just plug in our circuits again. And because Fourier is also differentiable, you can even use a fully differentiable version of our circuits, and then everything is differentiable. So essentially, you need a complex valued probabilistic circuit, but we can approximate by in-leaf for the real and imaginary part. We just take Gaussians. And that works pretty well. I mean, at least for the maybe simple domains we looked at, we can be better than LSTMs. But again, we're actually not saying we want to compete with LSTMs. I think what we want to say is combine. Take an LSTM and make, if you need probabilities, you can put in a Whittle network on top, and you get your both, I mean, the good prediction and a probabilistic estimate. So, and then we were wondering, spectral, there was time in machine learning when many people were working on spectral domains. So the fun part in densities is that there's also a spectral approach to densities, and that is called the characteristic function of densities. So think of a density as a time series, then you have the idea of running something like the Fourier transform, and that's what statisticians have done for you, and you can get all these characteristic functions. And why is that interesting? It's a mapping of a discrete distribution into the continuous space. So all of a sudden, you can deal with mixed domains all in the continuous space for free. And so that is what we published last year. So you just do what we did for time series, but now for densities using so-called characteristic functions, and you can get hybrid distribution or models in hybrid domains for free. So that is cool, but I was more interested in, can we make use of that for causality? Because somehow causality seems to be the real underlying concept in science. I mean, not that I'm a super expert there, but I like the idea at least. So we started in seeing, can we get also tractable models, or kind of tractable for causality? And this is what we did. So essentially, you can say that one of these probabilistic circuits is a bit like the density that you will get if you intervene somewhere. Now, you want to have different interventions, and you can control the different interventions by a neural network, controlling the parameters of your circuit. So you have a circuit plus a neural network. Is a kind of alternative to the work by Joshua Banjo, where they were looking at neural causal models. And so we now have a new neural causal model with a bit of a probabilistic circuit in there. Now that you have a circuit, what can we do? Well, we can also make use of a characteristic one, right? And that is amazing, because all of a sudden you get one of the first causal models that works in hybrid domains. And it doesn't matter whether the discrete random variable is a parent or a cause for a continuous one, or vice versa, which was classically always the problem. And I think this is where we have now started to get in touch with medical people and other physics people and try to do quite a lot there. So with that, let me conclude, and sorry for the delay, but I hope I have shown you that all the deep learning is amazing, the deep neural network. I mean, wow, who thought 5 or 10 years back where we are? But I think there are also alternative models where if we combine both, we get maybe even more out of it. So in that sense, I hope I just have told you that Nando, I respect him, but I think Nando is wrong, because we just started, and scale is not the only answer. We need many, many different models, particularly also models like spiking neurons and how to get them in there. And I hope you see now, think of the probabilistic circuit by replacing the leaves now with spiking versions, and sum and product maybe by a continuous approximation. I guess we can also get spiking circuits and then see where we can go from there. Thanks a lot. Thanks for your patience.
So, are there any questions in the audience?
So thanks a lot. So I'm Barbara Hammer from Bielefeld. So thanks for this like tour de force through making sense out of neural networks. One question is if you have sub-symbolic measurements, so the X, Y, Z don't have any meaning. So how would the transition be to like causal models? The one question, and the other is what about adversarials, because they would like occur from that.
Yeah, so about adversarials, so first of all, that is what we wanted to show here. You may suffer from adversarials as well, but the countermeasures might be tractable, so you might get a bit of a better argument why they are more robust. But of course, I mean, they are function approximators. Now, about the first one, if you just get data and if you have no idea how to connect to a symbolic variable, for now, you're screwed. I think there are some first ideas about concept bottlenecks, where together with an expert, you may get a bit of an interpretation. But yeah, you may get symbols that are not meaningful to you, and at some point for communication, you have to assign meaningful symbols.
So, Martin Lefebvre from UC Louvain, Belgium. I was wondering what you envision as being the challenges for the implementation of these types of model in hardware, maybe digital.
In hardware?
In hardware, like if you go to FPGAs or maybe to ICs.
Yeah, so for FPGAs, we did it, right? And then the main issue is that the computation becomes more sparse, but in an FPGA, you can do that slightly better than on GPUs. So what I would have in mind is to come up with a new circuit and a real hardware circuit. But sparsity is still an issue, so that's where some of the alternative to NVIDIA might help. And of course, all of you. I'm not the hardware expert here.
Thanks for your insights.
Thank you.
Just one very quick question. So in this ALICE program, do you also collaborate with people from the ethic labs?
So not in this specific program. In the ALICE programs per se, there are also ethics people. And I, myself, personally, I'm working a lot, at least with other people that publish at FACT and AIES. Yeah, so I do collaborate, and I have to check, maybe other people in the audience knows whether ALICE had a specific ethics program. I'm not sure. But we are fully aware, and me personally, I'm learning a lot from this. Sometimes it's hard, right? I mean, you have to swallow and say, oh yeah, indeed. Yeah, it's very worthwhile doing it.
Okay, thanks again,
Thank you.
Kristian, for your great talk.